Firstly, thank you, Somnath, for a very kind introduction. Also, let me start by thanking the organizers of this conference for actually planning a dedicated session on Professor Tanu Padmanabhan's contribution in astrophysics and cosmology. And I feel it's my privilege to talk about such a towering personality like Professor Padmanabhan and about his research results. So without really wasting any time, let's start talking about Professor Padmanabhan. Now, we used to call him Paddy, and this is the name he is known by in the astrophysics, cosmology, and the physics community. So for the rest of my talk, I will just refer to him as Paddy. So Paddy, who passed away last year, he was one of the most well-known theoretical physicists of our times. And when I say well-known, I'm not talking about well-known in India. He was well-known all over the world. He was internationally acknowledged for a cutting-edge research on gravitation and cosmology. Besides his research, he made immense contribution to training and education of young researchers. And a large part of his legacy actually lives on through various students and other researchers he taught, mentored, and collaborated with. He also has written a wide range of textbooks on various topics. And I believe all of them are very popular. Some are used for teaching undergraduate and graduate courses, and some are written at a popular level. Even someone who is not trained in physics can also understand and can feel the excitement of that field. Not only like training and writing textbooks, he actually spent a lot of time on science popularization, again through a series of articles in magazines and journals. In fact, very early in his career, he used to publish a comic strip, again outlining the story of physics over times. And of course, we should not forget about his contribution to scientific and academic administration, being part of committees and various organizations. And I will try to touch upon some of these aspects in my talk. And as Somnath also mentioned, I have a personal connection with Paddy. I worked for my PhD under him during 1998 to 2003, and that's how I came to know him. And he had been someone I looked up to throughout my career till the last day. So, a quick kind of overview on Paddy's life. Paddy was born in Trivandrum in Kerala, 1957, to a lower middle class family. His father was a school teacher and his mother was a homemaker. He did most of his schooling and college actually in Trivandrum. And he was interested in science, particularly physics and mathematics, from a very early age. In fact, I mean, this would give you some idea about the talent he held. And he wrote his first paper in 1977 when he was still in his bachelor's. He was doing his BSc, and you can see that paper published in Pramana, and it talks about solutions of scalar and electromagnetic wave equations in the metric of gravitational and electromagnetic waves. Of course, he did his MSc from Kerala University, finished in 1979, and then he joined TIFR in Mumbai as a PhD scholar, and he worked under, again, another very famous astrophysicist, Jayant Narlikar. And soon after he joined as a PhD scholar, he was offered a faculty position which he took up. So I think that happened around 1980. So he became a permanent faculty member of the Tata Institute of Fundamental Research very early, when his age was what, 23 or something like that. He stayed there for quite some time, and in 1992 he shifted to IUCAA in Pune. This was the institute again founded by Narlikar when he moved from TIFR to Pune. Besides all these things which I talked about, Paddy also held several visiting positions and adjunct positions and name chairs at internationally renowned institutions, both in India and abroad. And needless to say, he was a recipient of a number of awards, and there's no point in trying to list them in a short talk like this. One of the probably most famous ones would be the Padma Shri, which he received from the government of India in 2007. If we look at Paddy's interests in astrophysics and cosmology, so I mean, okay, so if I try to look at Paddy's interest, research topics, probably one can divide it into like two broad areas. One would be quantum aspects of gravitation, where he worked a lot, and the another would be the conventional cosmology and astrophysics. And in this talk, I will concentrate on the second aspect, on cosmology and astrophysics. Post 2005 or so, actually he spent most of his time on the topic of emergent gravity, again, which has to do with the quantum aspects of gravitation. So as I said, I won't be talking about this aspect. Although he did not work too much on cosmology at these later stages of his career, his research on cosmology is still very widely acknowledged. And that is something I would like to impress upon in this presentation. Now, again, if I try to list the research problems in cosmology where Paddy made significant contribution, again, it will be a long list, but probably a biased and a short list will be what I tell you now, is that he very early he worked on generation of what cosmological perturbations during the inflationary phase of the universe. He did work on statistical mechanics of gravitating systems. In fact, he has a review article on this, which many people find very useful. He spent a lot of time on cosmological structure formation, in particular numerical simulations and analytical insights, and I will talk a bit about this aspect of his research in this talk. He worked on what is known as the intergalactic medium. There is a lot of matter between the galaxies which exist in our universe. He worked on the nature of dark matter and dark energy, and I will spend quite a bit of time on these aspects of its work in this talk. So, before I can make you appreciate the importance of Paddy's work, I have to give some context. So, let me spend some few slides on cosmology and in modern ages what we understand about cosmology. So, cosmology in a nutshell refers to the study of the universe as a whole, and it asks very fundamental questions related to our existence. I mean, how did the universe begin? How does it evolve? How will it end? Why does it look the way it does? And as a result, it makes close connections between observations, the things which we can go and observe using telescopes, and theoretical modeling, where we understand the physics through our calculations on paper or now in computers, and how do we connect these two. So a lot of these interactions actually make up the way cosmology works. So basically, I mean, in a nutshell, modern cosmology would be that you go make observations of distant objects, galaxies, and maybe the vast empty space between them using telescopes, and then interpret the observations using known laws of physics. Maybe while interpreting these observations, your calculations will tell you something new, and then you hope that future observations will go and either verify whatever the predictions were or rule out. And then you go back to drawing board and work out the equations again. Maybe not a single person does it, but generations of scientists and physicists and astronomers will work on something, on one topic, and will build a picture. And that is what gives us our understanding of this cosmological model in the universe. So comparison between theory and observations in a fully quantitative manner using statistical tools is a very important aspect of modern cosmology. So as I said this, I just told you that you just test predictions of the theory with further observations. Now, what do we know about the universe today from various observations? So I won't have time to go into all the observations and calculations and tell you how we reach that conclusions, but I will place some facts which we know. So observations and calculations by Hubble and Lemaitre in the 1920s told us that we are living in a universe which is expanding with time. So basically they found that galaxies are moving away from each other. Now we understand in the framework of Einstein's relativity that it is the space which is expanding. So as these distant galaxies are moving away from us, this gives rise to the concept of expanding universe. And not only that they are moving away from us, they are not moving away from us in a haphazard manner. It turns out that the speed of recession is proportional to the distance to the galaxy. That is, a galaxy twice as far away will be moving away with twice the speed. Now, at early times, this would imply that the galaxies or points in our universe or observers in our universe were closer to each other. So if it is expanding now, if I go back in time, it would have been kind of collapsing and galaxies would be closer to each other. So this gives rise to the model where universe began from a very small volume. And this model is known as the Big Bang model of the universe. This is the model we think is what describes the observations we have till today and is the most successful model in explaining our universe as of now. Now, there are a lot of consequences, physical consequences of the expansion, and let me give you one example. That is the redshift of light. What I mean by that is, as the universe expands, if there is light traveling through the universe, its wavelength increases proportionally. So by the time the universe, let us say, becomes twice its size, the wavelength of the light will also become twice compared to what it was earlier, and similar, and so on. So if a light is emitted from a distant galaxy at some wavelength, it will take some time, maybe millions to billions of years to reach us. And by the time it reaches us, that wavelength of the light would have increased. So we will observe the same light, not at the wavelength at which it was emitted, but at a larger wavelength. This is known as redshift. Now, this redshift is extremely useful in finding distances to cosmological objects. Because this redshift in some sense is something which is directly observable and can tell you what the state of the universe was when the light was emitted from that distant galaxy. Of course, so this is how we learn about the universe at very early times. Now, there is another aspect of the Big Bang cosmology, of the expanding universe. What you can think about is, if you take some matter, let us say gas or radiation, and if you just compress it, reduce the volume, what will happen is the temperature of that system will increase. Now, because of the smaller volumes at earlier times, the universe would have been hotter at earlier times. And as it expands, it cools. Now, at very early times, the universe would be so hot that the particles we see around us, for example, molecules, atoms, electrons, protons, neutrons, whatever we are made up of, none of them would be able to form because the heat will essentially dissociate them. Expansion would lead to cooling, and then that will allow different particles to form for the first time in our universe. And depending on what the binding energy of each of these components are, that will determine when these objects form as a function of temperature of the universe. For example, we can ask the question, when did the atoms form? Atoms formed when the age of the universe was around 400,000 years. The energies became small enough so that the electrons and protons could bind with each other and form atoms. Now, before that, what would have happened was the electrons and protons would have been kind of free, would not be bound with each other, and the radiation would constantly scatter off the free electrons which are charged. So as a result, the photon may not be able to travel very large distances uninterrupted. So it will constantly get scattered off, like the way I have tried to show in this cartoon. Now at some point, once the atoms form, the universe will be devoid of all these free electrons, and these photons will be able to travel to us almost uninterrupted. They will be able to free stream. This radiation we can detect, and that is detected as the cosmic microwave background, or the CMB. Now the detection of the CMB actually was kind of a proof that all this story I am telling you, that the universe was smaller earlier times, it was hotter and none of these components were able to form. This story is correct. I mean, CMB was kind of a proof that this model actually works. And in fact, the discovery of CMB and various of its properties ruled out all the competing models, all the alternative models of cosmology. And it is only the Big Bang model which kind of survived. It survives still till today. Through a series of experiments and observations, we now have a very good idea about the history of the universe. So if I think about the universe like expanding as a function of time, and the time is flowing from left to right. So maybe at some point there was the Big Bang, and then there was a phase where the universe actually expanded rapidly. It is known as inflation. We think that inflation happened, but it is not something which is still observationally completely settled. This inflation ended and the universe started to expand at a slower rate. And at some point the protons formed. At some point the nuclear fusion begins, and the nuclei, various nuclei formed beyond hydrogen. And then came the cosmic microwave background, and this is where the atoms formed. And then we entered a phase which is known as dark ages, because there were no galaxies or anything. And at some point the galaxies and the first stars formed. And then we entered a phase which is the modern universe. And the age of the universe today is around 14 billion years. So this is the kind of cosmological universe we have. The constituents of our universe is also something which we can infer from a series of observations. So the Big Bang history is confirmed by several independent experiments over a wide range of frequency bands. And these studies, a combination of these studies, will give us a fair idea about how this universe expands with time and what its constituents are. Now this is basically a pie chart of the constituents of our universe. You can see only about 5% is made up of ordinary matter. Ordinary matter means the matter which we are made up of: electrons, protons, neutrons, and whatever is made up of these things, all our nuclei, all these higher order elements, everything you can think of, all the gas, atmosphere, all the galaxies, stars you see around. About 27% is something which is called dark matter. What is dark matter? I will talk a bit more about it, but in a nutshell, what is dark matter? We don't know. And then the story gets more mysterious. About 70% of the matter is something called dark energy. Again, something we have no idea. So you see, besides this 5%, rest of the 95% of the universe, or we simply don't understand. Okay? And this is something which Paddy spent a lot of time trying to understand, what these mysterious components could be. What do we need to understand them? What kind of observations? What kind of theory? And the thing is, we still don't have answers to that. And I'm sure had Paddy continued, he would have actually made a lot of breakthroughs in the future. Now let us take these components one at a time. These mysterious components, dark matter. So the dark matter is something which is like ordinary matter otherwise, but except that it does not interact with light. So we know about dark matter, for example, from observations of galaxy clusters. So these are like a group or a collection of galaxies in our universe. And they indicate that there is matter which we cannot see beyond the stars and the gas that exist in that cluster. So this unseen matter is what we call dark matter. Galaxies like ours, the Milky Way, is also surrounded by dark matter halos. Again, something we know using observation. So if our galaxy, I mean, this is a cartoon diagram. If you think our galaxy is somewhere here, there is a huge dark halo, which we cannot see. It is not absorbing or emitting light, but we know about its existence from its gravitational, basically, presence. It will affect the motion of other particles because it has gravitational attraction. It will bend light if light passes near this dark matter, and through such kind of observations we know this dark matter exists, but we don't know what it is made of. It is something, it's not something which we have detected in our laboratory or in our terrestrial experiments, in our particle physics experiments. Paddy actually did a lot of work. For example, in collaboration with Vasanti, he used observations of galaxies and groups and clusters to understand the nature of dark matter. For example, whether neutrinos can contribute to dark matter. These are some work which they did in the mid to late 1980s. Of course, now we know that these neutrinos cannot be dark matter, but at those times, these kind of calculations were very important because people were not sure about the nature of dark matter. The composition of dark matter is still an unsolved problem. Several experiments, both from the particle physics side and from the astrophysical side, are ongoing and are being planned. And the hope is that in the near future, we will have some idea about what dark matter is made up of, but one can never be sure unless it is experimentally detected in these observations. So this is about dark matter, and as you can see, although Paddy worked on this quite some time back, the questions he was trying to address and the methods he were using were still quite relevant. And this is the theme which you will see will be repeated throughout and throughout my talk whenever I talk about Paddy's contribution to cosmology. Now let us talk about another mysterious component, which is the dark energy. Now, in the presence of gravity, the expansion of the universe must decelerate, and this is something which we understand and we can show using equations. So the rate of change of expansion, that is the speed of expansion, must decrease with time. And this is entirely because of the attractive nature of gravity. However, there are observations, and there are these famous observations of supernova type 1a, which allows us to compute the speed of expansion as a function of time. So what I have plotted here is, in the y-axis, I have plotted the speed of the expansion versus in the x-axis, I have plotted what we call is the size of the universe, but you can take it as a proxy for time. Now these will be earlier times and these will be late times, and you can see, and the green points are essentially the data. I mean, these are some data but processed in some way. And you can see, if you look at the green points, and by eye it is clear that at earlier times the green points indicate that the velocity or the speed is decreasing with time. That is deceleration. But at some point, this deceleration stops and the universe starts to accelerate. And this is a mystery. The universe should not accelerate if it is made up of like normal matter, like which we are made up of, including dark matter. Even dark matter cannot make the universe accelerate. Now, this data basically is showing that it is accelerating. So something is mysterious here. In fact, this plot is something, I mean, there are many ways of showing that the universe is accelerating. But Paddy found a very unique way of showing it. I mean, he actually took the data and converted it into this, what we call a phase plot, a velocity versus position plot. And the fact that the universe was decelerating earlier and then started accelerating became so obvious from the way he plotted it. So this is from a paper we wrote in 2003, but then it was updated because new data points came. And I believe there are more data points, but the main conclusion still remains the same. This explanation for accelerating universe requires a component which has negative pressure. Now, we don't know of anything which has negative pressure. And this is basically this mysterious dark energy. This result was so important and so path-breaking, this it led to a Nobel Prize in 2011 to three people, Perlmutter, Schmidt, and Rees, for their efforts in doing these observations and then trying to interpret them. Paddy, as I said, spent a lot of time understanding the nature of dark energy. So there is one aspect where he looked at the data and found a way to clearly show that this data implies acceleration. The second part is to figure out what gives rise to this acceleration. So this nature of dark energy, I mean, what is this dark energy made up of if it is not something we know? For example, he worked a lot on the string theory inspired fields called tachyonic fields, which became very popular in the early 2000s. He looked into whether these tachyonic fields can act as dark energy. Now, the most popular explanation of the accelerated universe is the cosmological constant. However, the cosmological constant is something that even if the universe does not consist of something, even if it's like a vacuum, that vacuum may contain some energy. The vacuum will have fluctuations, and that fluctuations will contribute to that energy. And it turns out that that component of vacuum energy will have a negative pressure, have an effective pressure which is negative. This would have been ideal for explaining the acceleration of the universe, except the observed value is too small compared to what is understood from the fundamental physics. So it doesn't simply work. In fact, in 2003, Paddy wrote a detailed review article. He named it Cosmological Constant, the weight of the vacuum. And again, a very useful literature for people who work in this field. He covered various aspects of observations, theory, and what can be speculated in the future. For example, he explored whether the cosmological constant is a stochastic variable. So it's not the way people think about vacuum, but something which is probably stochastic and has to be interpreted in a probabilistic way. Much later, he also tried to see whether the cosmological constant can be related to the information accessible to a cosmological observer. Because a cosmological observer cannot actually look into the universe as a whole, because there are horizon effects. The age of the universe is finite, so light can only travel a finite distance. So the fact that the cosmological observer doesn't have access to information, can it kind of mimic as a cosmological constant and hence give rise to dark energy? So these are really speculative ideas, and he did some preliminary work on all of these. Probably if we had got some more time, he would have tried to make it more concrete and solid. But till now, even now, we still don't know what it is. So the nature of dark energy is still unsolved. And in fact, several cosmological surveys are ongoing and being planned, which will map out the universe to very high precision to understand the properties of dark energy. Again, you see Paddy was working on something which is still very relevant. I mean, people are still trying to understand what this dark energy is. And as I said, I'm probably repeating myself, but I'm sure Paddy would have contributed a lot if he was around. The other thing Paddy actually investigated quite a bit is constraining the values of the cosmological parameters. So now we have a concordance cosmological model which can be described by a set of parameters, and these are constrained by a series of observations. So at very early times, Paddy used several different observations to put constraints on these cosmological parameters. And in fact, they could deduce the presence of dark energy just using different combinations of observations, even without the so-called supernova type 1 observations. So in fact, they named this article Crisis in Cosmology. And in this graph, I have tried to kind of show what they meant. So in the x-axis, the horizontal axis, he plotted the amount of cosmological matter that is present. And one would be that the full universe is made up of like normal matter, including dark matter. And this is the vertical axis is the value of what is called as the Hubble constant, which measures the expansion rate of the universe. And from a series, and the different curves show basically constant coming from different observations. And if you just combine these observations, they could show only this hatch region would be allowed by them. And you can see the hatch region is not consistent with the matter density being equal to 1. So clearly, there has to be something which is not this conventional matter. There has to be something which is unexplained. And they could actually deduce about dark energy from these series combinations of observations. Later, when I was working with him, he also looked into great detail into the supernova type 1a data sets. And he tried to see whether different data sets, at that point, different people were actually giving out different kinds of data sets. And he was trying to see whether the data sets are consistent with each other. And we found some interesting results. Of course, later on, the data sets have become much more sophisticated and people could iron out the differences these things have. But we were able to show that these data sets need some work before we can start to basically interpret them naively. In fact, I mean, if you look at the cosmological parameters today, just like the accelerating universe or the dark energy was termed as crisis in cosmology in the 1990s, there is a similar crisis in cosmology today. The expansion rate of the universe, as measured from different kinds of experiments, show an inconsistency. So this is shown in this plot. This is a much more recent plot. This is basically the value of Hubble constant as measured by different experiments shown in different colors as a function of year in which the experiments were made. At earlier times in the 2000s, the experiments, all these experiments had large error bars. So the value of the Hubble constant from different experiments seemed to be consistent with each other. But as the experiments become more and more sophisticated and precise, they seem to kind of rule each other out. So you can see the blue one, which is coming from something known as Cepheid variables, that is observations of a nearby universe. And the black one are the experiments, the observations coming from CMB experiments, which is looking at the universe at very early times. They seem to be not consistent with each other. There is another set of experiments, the tip of the red giant branch, that is falling somewhere in between, but different experiments seem to be giving different answers. So this is something which we don't like in cosmology, and we are not sure what's going on. So maybe this have to do with some problem with the observation. There is some systematics in either one or all of the observations, or maybe there is some physics beyond the present Big Bang model. This is something Paddy would have loved to go and look into great details. The fact that there seems to be something missing in the cosmological model, and whether it needs some more inputs from the physics side is something would have been very, very interesting for him. For the next few slides, let me talk about something which Paddy actually also spent a lot of time working on. And to motivate that, let me just go back to the CMB. The early universe, as far as we understand, was very homogeneous, and the matter in the universe was extremely smooth. And this we know from the observations of CMB. This is that light which is left over from Big Bang, as I was talking about earlier. And the CMB reflects the state of our universe like about 400,000 years after the Big Bang. This is like the universe was baby compared to what it was today. I mean, today its age is 14 billion years. So it is orders of magnitude smaller, than, younger than what it is now. And if you look at the cosmic microwave background from coming to us from different directions, as long as we subtract out the local motions, the CMB seems to be kind of very smooth. However, if we go and look at the same CMB with like more sensitive experiments, we detect very small fluctuations in those, about 1 part in 100,000. So it is really, really small. And these fluctuations, you can think of them as the seeds of all the structures we see around us today. Structures means all the cosmological structures we see around us today. So what do I mean by cosmological structures? So what I have shown here is a galaxy survey. So this is observed using a telescope from Earth, and each point in this plot basically is a galaxy. Now you can see these galaxies are there, many of them, but they are not distributed in a random manner. There seems to be some kind of a pattern. You can see there are regions where there are many galaxies, and then there are regions which are void of galaxies, which we call voids. And then you can see there are these filament-like structures. I mean, it seems there are like collections of galaxies, and in between some small number of galaxies is making some kind of a bridge or a filament. So this whole structure is popularly known as this cosmic wave, a very rich structure in the universe we see around us today. Now, this is the universe which is like we see around today. And one question to ask is, if the universe was almost smooth at early times, as is implied by the CMB observations, how did all these structures come into being? So how did these structures form? So this is one of the very fundamental questions Paddy tried to understand. The basic idea is that these structures form because of gravitational attraction, which is not very difficult to understand. But the question is, can we get the kind of quantitative predictions right? Can we solve our equations? Can we solve our mathematics and go and make quantitative comparisons with what we observe and get everything matching? In fact, in the 1990s, he developed with the Jasjit Bagla one of the very first n-body simulations. So these are basically, you are solving for the gravitational kind of evolution of cosmological matter in a computer. So you simulate a volume of our universe. So you start with something which is very kind of homogeneous and smooth, and let the collection of these cosmological objects kind of evolve under gravity, accounting for the expansion, of course, and then see what happens. And actually they saw these nice patterns coming, I mean, in their simulation box, which would, I mean, if you go and compare with observations, would actually match in a full statistical sense. And using these kind of simulations, several interesting problems in gravitational clustering were attempted by Paddy and his students, in particular Jasjit Bagla and Sunu Engineer, who spent a lot of time in developing these n-body simulations. And now again, this is something the field has moved so far ahead. I mean, there are so many people who have now made simulations, and they are all over the place. I mean, there are many simulations which are there, and many of us go and try to understand them. And this, for example, is a movie which shows how the large scale structure form, and this is run using a simulation called Gadget, which is publicly available, but there are many such simulations available. And you will see that at earlier times, this is the earlier times when the universe looks very homogeneous, and then you will see slowly this cosmic web is starting to form because of gravitational attraction. And so you see these whitish regions are where the galaxies will from, the bluish regions will where the voids be. There are many examples of recent n-body simulations, and some of them are listed here. And here I should also stress that the group in IIT Kharagpur is also one of the leading groups which develop this kind of n-body simulations and follow it up with various other interesting studies of galaxies. But again, this is something Paddy worked so early, and it is still, those works are still very relevant. There are again some of these simulations, some of these very popular simulations are also kind of publicly available. People can go either download the simulation code and run them, or in some cases they give you the data. They have run it using extremely large supercomputers, because these are also have become very computationally expensive, and you can get the data and then start to interpret them. In fact, Paddy had a very different approach to use simulations, and in Paddy's web page, there is a line that I mean, using simulations is important because some people in this field use computers the way drunkard uses a lamppost, for support, not illumination. And Paddy wanted to use his simulations for illumination. So he always combined these very high numerical simulations, this highly compute intensive numerical simulations, with analytical methods to gain insights to the underlying processes. For example, one of the things he worked on is called nonlinear scaling relations, just to find a way to explain the nonlinear regime of gravitational clustering, which is otherwise very difficult to do analytically. Later, he also developed semi-analytical models to understand the intergalactic medium. So this is the space between galaxies. So galaxies, as you saw, they come in bunches. So they leave a lot of space in between, which is kind of containing diffuse gas. This is known as the intergalactic medium. And he developed analytical and semi-analytical models and coupled them with simulations, again in the early 2000 or so. And in fact, some of these models which we developed in collaboration with Paddy, we keep on still using them, although Paddy has moved on to something else. And I couldn't help saying that, I mean, the code which we developed in early 2000, we are using it till now. I mean, even today as we speak. And we put a preprint yesterday, which uses a code which was written in collaboration with Paddy in the early 2000s. So again, I mean, Paddy had some kind of, genius ability to identify problems which would stay relevant for years to come. Even though he may not be working on it and he may have moved to something else, maybe his students kept on working on them, or somebody abroad or somebody somewhere else picked up those problems and kept on working on them. Why? Because these problems are very relevant, they are very interesting, and this is something which we would like to have an answer to. Paddy also, as I said, wrote several books on cosmology and structure formation. For example, this book, Structure Formation in the Universe, was one of the first books on the subject. When Paddy wrote this book, there was almost no book available which talked about this structure formation in the universe, how these small instabilities grew and formed. So he actually worked out the full mathematics of this subject and put it in this book. And many of us, when we started our PhD, would go through chapters of his book, work it out to make us understand about what this topic is all about. He then also wrote a book which was a very different kind of textbook. He named it Cosmology and Astrophysics Through Problems. So this is not a conventional textbooks which actually develops the subject as chapters. This would actually develop the subject by giving problems to the student or the reader who wants to read this book. And then in the second half of the book, he would actually try to give hints to how to solve these problems. So you can learn the whole subject through problems. Again, a very interesting way of teaching maybe. Later, he came up with another set of books, which I feel it's probably one of the most important contributions of Paddy, which is to write a book on theoretical astrophysics. He called it a course on theoretical astrophysics. So this is a 3-volume set of books. So first volume was on astrophysical processes. The second volume was on stars and stellar systems. And the third volume was on galaxies and cosmology. And then there were several other books which I did not talk about because I thought these were probably the most interesting textbooks which students still use. And in fact, if you look at the first volume of theoretical astrophysics, you will realize what kind of physicist, what kind of complete physicist Paddy was. So what I put out here is a table of contents of the first volume of theoretical astrophysics, which basically talks about the physics you need to understand astrophysics. And you can see it contains almost all branches of physics, starting from dynamics to special relativity to electromagnetism, statistical mechanics, plasma, general relativity, nuclear physics. Almost all branches of physics are touched upon. Now, only someone like Paddy, who had hold on like the whole range of physics, could write such a book. This also gives an idea to students who want to do astrophysics as to what kind of expertise they need. It will be good if they can go and learn the basic physics and almost all branches of basic physics quite well, because astrophysics really needs all branches almost equally. So this is where I find the way Paddy structures this book, conveying this idea to students becomes very easy if I give this book to a student who is starting on theoretical astrophysics. But was Paddy just a theoretical physicist? Actually, his contribution go well beyond theoretical physics. I mean, he may not have written books on these subjects, but he did a lot of work. For example, the government of India actually set up an advisory group to facilitate India's entry into one of the international collaborations building the next generation of large telescopes. So this happened in 2008 to 10, and Paddy was asked to be the convener of this advisory group. So the role of this advisory group was to tell that there were many international collaborations which were trying to build these big telescopes, the next generation of telescopes. So what would be India's role in them? Should India join one of those collaborations? And if yes, which one should it join? And this group and then later other discussions ultimately led India joining the 30-meter telescope or the TMT collaboration, which is again a very large telescope which is going to come up in the next decade, and it will enable kind of next generation cutting edge science for Indian astronomers. So again, you can see Paddy going well beyond what we think of as theoretical physics, but actually working out as a convener of the group, what kind of observational facilities should Indian scientists have access to. Similarly, there is a telescope called Giant Meter Wave Radio Telescope, GMRT. That is one of the largest radio telescopes in the world, working at low frequencies. This is a telescope which is near Pune, 80 kilometers from Pune. And it is like one of India's success stories as far as observational astronomy is concerned. And Paddy was kind of very closely involved with GMRT because, maybe one of the reasons why he was in IUCAA, and the institute which made and kind of maintains GMRT, runs GMRT, is called NCRA, where I work, and that is just across the road from IUCAA, so it was physically very close. But Paddy served as the chair of the time allocation committee of the GMRT. So this is the committee which will look at all the proposals which come to observe with GMRT and will decide which of the proposals are worth giving time to. So again, this is something where Paddy was going well beyond his comfort zone of theoretical astrophysics and doing something for observational astronomy. And GMRT also, it acted as a stepping stone for India to join another international mega project, just like the TMT I told. This international mega project was in the radio wavelengths. It's called the Square Kilometer Array, or the SK. So maybe that brings me to the kind of end of the talk, and let me just kind of summarize by talking about Paddy's legacy in astrophysics and cosmology. And I think Paddy had a very unique way of identifying the most relevant, interesting, and challenging problems, and that led him to work on many diverse areas of research, and most of them are relevant even today. Many astrophysicists and cosmologists in India and probably abroad were taught and mentored by Paddy, and they are keeping like the Paddy's legacies alive, continuing. And beyond his research, Paddy's interest in pedagogy, for example, his textbooks, his YouTube lectures, his review articles, they all help, not only help, they keep on helping training generations of physicists, and it will probably keep on happening throughout. Paddy also contributed immensely to India's involvement in international mega projects to big telescopes, so that is kind of beyond his role in theoretical physics. So you can see his wide contributions in astrophysics and cosmology, and I think he will keep on being relevant for long times to come. So let me end on this note, and I thank you all for listening to me. And if there are any comments or any questions, I will be happy to take.
Thank you very much, TIRTHA. Are there any comments, questions anybody would like to make? Prashanto has a question. Mike.
I am not in the field. Just I wanted to know that if universe is expanding and that is cooling is going on, so why we should be worried about this global warming? Global in the sense I am talking about universe warming. Is it universe warming or it is only Earth is warming?
No, yeah, it's only the Earth. So these are completely different scales. So the universe is cooling and will keep on cooling at cosmological scales, and we exactly know how it will cool throughout. I mean, the temperature actually goes as 1 by the scale factor. So if the universe size doubles, the temperature will be half. But this is the temperature averaged over the whole of the universe, the cosmological scales, and this is how it goes. And again, I was probably not technically very accurate here. When I talk about the temperature of the universe, I'm talking about the temperature of the radiation field, because the temperature of the gas cools differently, but even the temperature of the gas will also cool when I average over the cosmological scales. But that doesn't mean at small scales things are the same. In fact, at small scales, for example, two galaxies can come towards each other. The galaxies which is closest to us is Andromeda, is coming towards us. Why is that happening if the universe is expanding? That is happening because of the local gravitational force which has overcome the expansion of the universe. So what I'm trying to say is the local physics, when it starts to dominate, it can give rise to something which is completely different from how the large scale universe or the average universe is behaving. So things can come close to each other, things may get hotter and so on. Okay, but the large scale universe will behave in a certain way. The small scale universe may behave in a completely different way.
Does anybody else have anything they would like to? Yeah, there is another question there.
I had one question which might be silly. If the universe is expanding, that means also our bodies are expanding and everything. Everything is expanding, right? Down to the atomic level. Not? Okay,
No,
that's one part of the question. Second part of the question is, if the universe is expanding, would the stars around us appear to be further and further? Does the space between expand, and that so that visibility or size would appear less to us?
Yes. So no, this is actually a genuine question, and it requires some explanation. So the first answer is no. I mean, we are not expanding. The Earth is not expanding. Probably even the galaxies are not expanding. Stars within galaxies are not expanding. It's only the distance between galaxies which are increasing. So yes, the underlying space is expanding, but there is also the gravitational force and various other forces which are playing a role. And for example, why are we why do we have the size we have? I mean, why are our sizes whatever it is? Because there are forces acting and they are kind of put us in an equilibrium. The forces of gravity might be trying to squash us, but there are kind of electromagnetic or solid state forces which are kind of acting against it, and hence we have all these stable systems. We are stable, the furniture around us are stable, the Earth is kind of stable, so are the galaxies. So something which is stable is determined by a set of forces, all physical forces acting on each other and giving us that kind of stable structure. And once that stability is achieved, that system is not expanding anymore with the universe. Things which are free, where, for example, none of these forces are very prominent. For example, two distant bodies. Basically, the gravitational force between them is negligible because of the distance, and they are all electrically neutral, and so no other forces are acting. These bodies can actually expand with the universe and go away from each other. But the moment other forces start to play a role, this large scale expansion is not valid anymore. We reach something which is kind of physically stable. So that is the reason why we are not expanding, atoms are not expanding. Even the stars in a galaxy are not going away from each other, because the galaxy has also reached a kind of equilibrium because of the equilibrium between the gravitational and other kinetic forces.
So you're saying that the gravitational force and this expansion force, which we don't know what it is just is expanding, are in a kind of competition or in a kind of juxtaposition. But if we don't know what it is, then how do we know that there's some kind of an interrelationship? Wouldn't the dark energy or whatever is causing the expansion of the universe, and since it's not interactive with gravity, since there's so much of the universe is not interactive with gravity, that would mean that that expansion is independent of gravity or anything else?
It is slightly more subtle than that. This expansion, okay, I mean, what caused this expansion, we don't know. But I mean, this is where it becomes a bit technical, but the equations of gravity allow for some space to be expanding. And we really don't, I mean, this is mathematically completely consistent. But yeah, I mean, so this expansion keeps on happening, and as I said, I mean, this we can easily understand in the framework of Einstein's general relativity. But yes, there's always a competition between this expansion and the gravity, which is trying to pull things together. The expansion is trying to take away these things together, and the expansion rate, how this expansion happens, is basically determined by the gravitational forces of all the matter that the universe is made up of. So it's not like the expansion is completely independent of gravity. So if the universe was made up of less matter, it would have probably expanded faster. It would have expanded faster and vice versa. So yes, so in that sense, they're coupled.
Yeah, Tirtha, can I add something?
Yes, yes.
Yeah, you see, the picture is like this. If you average the universe on some, no, I'm answering your trying to answer your question. Yeah, so if you look at the universe on some very large scale and you average it out, for example, the density of me is like the density of water, right? 1 gram per cc. But if you look at the average density in the room, it is a bit lower, quite a bit lower than that, because there are only a few people here, not the whole of space is occupied. Similarly, if you look at the entire universe and ask what's the average density, it is extremely low. Some 10 to the power minus 36 kg per meter cube. I mean, the density is lower than the best vacuum you can ever imagine. Okay, and it is on that scale that we have the expansion of the universe. It's on when you average it out over a very large scale. Now, if you look at it at small scales, there are regions of the universe where the density is much larger. Those regions, the matter is sufficiently dense to have overcome this expansion. The gravity is sufficiently high in this small region that it no longer expands. Okay, but if you look at it on some large scale, there are only a few very dense regions and much of it is vacuum. So on the average, it has a very low density, it is expanding. Okay, that's the basic thing. The laws of physics are same wherever you apply it.
Would mean that the galaxies are visually, for our human eyes, receding from us, and that the sky would be not as bright as it was, say, 10,000 years ago.
Yes, that's true. Yeah, the sky would be brighter would have been brighter in the past. The whole universe would have been hotter in the past. That's what he was saying.
Referring to when we're talking the last few days about cosmology and how it affected the people in terms of their construction of things like the Stonehenge.
Right, right. But this is on a very large scale.
Right. But
large time scale, not only large scale, on a large time scale. So you see the age over the human lifetime or recorded human history, this expansion is practically negligible. It's there, no doubt.
It wouldn't be very much then.
It is there, but it is extremely small, even less than 1%, less than a fraction of 1%. It is there, right? People are talking of measuring it over a human lifetime, but over the lifetime of civilization or recorded human history, let us say 100,000 years. See, we are talking about 16 billion years.
Yes.
Right. And when we talk of human history, maybe at most, I mean, even if you stretch it 100,000 years, right, that is 10 to the power 5 and 16 billion is 10 to the power 10, right? So 10 to the power 5 difference, order of magnitude. Okay, so you see the time scales are quite different. Okay, anyway, there's one more question, Tirtha.
Yeah.
Yeah, thank you, sir, for the talk. Sir, I had a question that, what kind of physical process might have went on? I mean, are there any existing theories that explain the physical process that might have went on from the smooth matter distribution in the early time to highly structured galaxies that we have now? And
yes.
Does this physical process dictate in some way the existing geometry of our galaxy?
Okay, let me answer the first part first. Yes, the physical process is actually very simple. So imagine you have a density field where, I mean, it's not completely smooth. You have very small density fluctuations like what we see in the CMB sky, 1 part in 10 to the 5 or even smaller. Now, if you have a region which is slightly overdense compared to the average, because of the nature of gravity, that region will attract more matter than the average, than the surroundings, let us. So that overdense region will start to become more overdense because it is attracting matter from the surroundings. And the surrounding matter, where it was probably slightly underdense, will actually, matter will go away from there. So the underdense regions will become more and more underdense. This is a peculiarity of gravitation. The moment you introduce some small fluctuations, gravitation will take over and amplify them. The name for this is gravitational instability. So it is not, in some sense, it is not very difficult to form structures from small fluctuations. Okay, so physically it is fine. The problem is just to do it correctly, in the sense you should not make too many structures than what is observed, and you should not make too less structures than what is observed. And you have to do this in a background expanding universe. So it is the numerical and quantitative calculations which are challenging, but the basic idea is not at all very difficult to understand. Even in the Newtonian framework, it is very easy to understand. And yes, I mean, how these things grow and bring out this large scale structure is something which we now understand using simulations. So, yes.
Thank you, Tirtha. So thank you, Tirtha, for this very. Yeah, there's one more question or some comments. Please come.
Professor Chowdhury, an observation first. This is Joy from IIT Kharagpur, and absolutely thought-provoking, and it's like a tribute to your guru, Thanu Padmanabhan, Paddy, Professor Padmanabhan. So in that sense, it brings not only cosmology, but a whole flood of respect and reverence to the master, to the legendary professor. That's my observation. As a very layman and someone who knew up to school level physics, and then after that reading a book by Steven Weinberg, the first 3 minutes, if I'm right, and then probably a few years later, another book, A Brief History of Time by Hawkins, if I'm right. So some questions had struck a fairly illiterate person like me. So two questions spring from that understanding and misunderstanding, somewhere in between. One is that somewhere I read in the second book that Stephen Hawkins is talking about multiple universes. Somewhere in some page he talks about multiple universes. I mean, initially I did not get him, but then I read at least 5 or 6 times those 3-4 pages towards the end of the book, and I felt like the universe that we are talking about is in a certain time frame with a certain event horizon, with a certain space fixation, with a certain time, what Professor Bharadwaj was talking about, about 15, 16 billion years. So the question one is, I mean, how do you explain this multiple universe, if it's actually valid or not? And the second thing, going back to the first book, which is by Steven Weinberg, I read long back, it's a pretty old book, and where the first 3 minutes, I think it's the whole of Big Bang, am I right? Yeah. So,
yes.
And I remember another book by the famous physicist, Professor Ashok Sen, who also talks on, worked on Big Bang, string theory, Ashok Sen, yeah.
Yes.
So I not a book, I read a paper by him, more of a popular paper, which came out in some popular journal, definitely a recognized journal. So he said there's a problem in physics, which is about the backward and the forward linkage of time, because the Big Bang assumes a starting point, and it proceeds from there towards, it's like a one-way arrow of time, and physics is questioning the other arrow, like dissolutions of universe, which is obviously the black hole. So things like that. So if I repeat, I mean, what is your take on this multiple universe? One, and is there anything like the 2 arrows of time? Is that considered in cosmology yet, or is it something which is yet to be considered in the future? I mean, but the questions are very immature. I mean, from my level.
They are definitely interesting and thought-provoking.
Yeah.
Yes, so multiverse is again something which is very it's in a very speculative state, I would say. And till now, we don't have really kind of observational evidence which indicate towards a multiverse. I mean, the presence of other universes or something which is beyond our observable universe. I mean, that is where, I mean, from a completely physics point of view, where we are basically interested in things which can connect to observations. The multiverse theory still remains a very interesting speculation, and it is very difficult to connect to something which we can calculate, predict, and then compare with observations, and so on. About the arrow of time again it's a very kind of subtle and complicated
The
kind of concept
multiverse supports time travel, isn't it?
I mean, I don't know.
In
I
that
don't
book,
know.
what he is suggesting, that book.
Yeah,
I
I'm
don't
just,
know.
reading out. I'm just reading out from those books. I mean, I'm barely suggesting anything because I don't have that acumen, you know. So, yeah. But I've seen these in Professor Ashok Sen's book. I think it was like a 25-page. Yeah, beautiful
Yes.
pictures. The wall.
I mean, the arrow of time is interesting in the sense, I mean, all the equations we write in physics are symmetric in time. I mean, I mean, they work the same way as we go forward or go backwards. But we still know that there is a time which goes in the forward direction. And that probably has to do more with thermodynamics, because that's the only theory in physics which clearly says that I mean, a system will move from one state to another. The probability of a system moving from one state to another is more from going backwards. So that probably sets up the arrow of time. And since you have asked, in fact, Paddy himself worried quite a bit about these things, and he probably he could relate some of these things about to choosing the initial conditions of our universe. So basically, the equations are symmetric in time, but depending on what initial conditions you put, one of the solutions will be preferred. And that is basically taking us forward in the time, and we are living in this universe as we live in. If there was a universe which started with a different initial conditions, it would have just looked very different from our universe. So the equations remain much more general. It is the initial conditions which give us the universe which we are living in. So again, I mean, yeah, the thing about many of these things are we haven't yet reached a stage where we can connect to observations very easily. So we have to kind of live with what the observations we have. And as a result, our understanding has also it also has its horizon, and it cannot go beyond there's a place where our understanding also stops. So as we go forward in time, as our physics improves, our physics knowledge improves, maybe some of these things will become clearer.
And that intrigues me to ask one extra question, which
Sure.
I have just framed by standing here. I read another book by a physicist called John Cramer. And there he talks about, or he predicts some kind of relationship between the wave equation by Schrödinger, and he says, knowingly or unknowingly, in the wave equation there is a binary, there's a couplet in which the half of that binary suggests forward linkage of time, whereas the other half suggests the backward linkage of time. But we use the wave equation without being aware of that, of that binary. And he says there is an inherent connection between the wave equation and the cosmology that we normally talked about. That's a very recent book which has come out. I'm just forgetting the name of the book. It's about it's on quantum physics. It's on quantum physics. Yeah, I think it's something on non-locality and universal function, something like that. John Cramer. Yeah. So
Yeah.
So that's
Yeah. No, so sorry. No, I'm not aware of this book. But whatever you told sounds very interesting. And just like cosmology and general relativity, quantum physics itself brings its own sets of like there's ideas which kind of goes against our common sense. So yes. I mean, I'm sorry. I can't really respond to this because I haven't read this book, but yeah, it's something
actually
which
Somnath,
sounds interesting.
Professor Bharadwaj is my old friend. We are from the same hall, IIT Kharagpur. So I think
I see.
in our wings, whatever physics was developed at that point of time, about 3.5 decades, I think we have somehow remained at that same stage with that same understanding, with the same questions, but definitely a lot of things have advanced. The observation scales have advanced. The understanding of the universe has really expanded, and the Nobel Prize that you just mentioned in your presentation is
Yes.
is of great importance. Great importance. And Paddy's involvement in much larger, deeper resolution telescopes as a doer, just not as a theoretical physician. Thank you, Professor Chowdhury. It was absolutely brilliant.